we've spoken about complex manifolds, and now I want to speak about almost complex manifolds, or more precisely, almost complex structures. So these are beautiful constructs. So let's first of all speak about the complex plane. But instead of thinking about the complex plane, think about it as R2. So at every point in R2, we have the rotate by counterclockwise by 90 degrees map, which is a map from the tangent space of R2 at that point to itself. Right? So I'm at a point P in R2 and I have a little vector starting at P. So it's living in the tangent space at P. And I can just rotate that vector by 90 degrees counterclockwise to get to JV. So at every point I can do that, right? And here's a nice little lemma. It tells us that a smooth map from R2 to R2 is holomorphic when you think of it as a map from the complex numbers to the complex numbers, right? If and only if the derivative of f applied to JV is equal to j applied to the derivative of f applied to v, right? At all points in the complex plane. So just to be clear, so I've got this map from R2 to R2, and so at every point I can take its derivative. That's going to be a map from the tangent space at that point to the tangent space at the image. So for example, it would send v to f lower star v. That's another notation for the derivative of f applied to v. And what we want here is that I can first rotate and then apply the derivative, or I can apply the derivative and then rotate. And these two things are equal at each point P. Or if they two things are equal at P, then we say the map is holomorphic at P, and it's holomorphic on the whole plane if it's holomorphic at every point in the plane. So that's the claim. So it's a way of characterizing holomorphicity in terms of this J map. So it's sufficient to check this on a basis for the tangent space. Right? I'm supposed to check it for every vector in the tangent space. I might as well just check it on a basis. So I've got these del x and del y basis vectors. Those are just the vectors pointing in the standard E1 direction and the standard E2 direction. So you notice that when I rotate del x, then it's going to rotate into del y. And when I rotate del y, it's going to rotate into minus del x. Okay, good. So take my function, which is a function from R2 to R2, and I can think of it as its first coordinate. That it spits out, I write that as u, and its second coordinate, I write it as v. And let's calculate these things. So if I first apply j, so let's calculate it on del x. So first of all, I'm going to apply j, and then I'm going to apply the derivative of f. So when I apply j to del x, I get del y. Then I apply the derivative of f to del y. We already shown in the first lecture how to compute derivatives and everything. So if you've forgotten how to do that, go and review that. But you'll agree with me that you're going to get out this. Okay. And in the target. So that's what I'm going to get out over here. I'm calculating this guy here. It's going to be a certain thing times del x plus a certain component in the del y direction. And those are these two components here. Okay. They got to do with the partial derivatives of u in the y direction. The reason I'm differentiating in the y direction, so not u, but the partial derivatives of these components in the y direction. The reason I'm differentiating the y direction is because I'm seeing what happens when I move in the y direction. That's what del y is, right? It's moving a little bit in the y direction. So then I'm just seeing what happens when I move in the y direction. So I have to compute these derivatives. So that's what this composite does. Let's do the composite in the other order. So if I first compute the derivative and apply it to del x, then I'm going to get this, because now I'm changing x, not y. And now I've got to apply j to this. We agreed that j acts like this. So I apply that in here. I'm going to get this. So in other words, if I say that f star j del x equals j f star del x, then it's saying that this equals this. And so if I equate corresponding coefficients here, that means that this must equal that. Similarly, this must equal that. which is what I'm saying here. And look, those are precisely the Cauchy-Riemann equations. Okay, but before we come to that, let's just see what happens here. I just computed this equation on a single basis vector, the del x basis vector. I should also check what happens when I compute it on del y. If I do that, you'll get out the same set of equations. Okay, so we've just found that this condition here in the theorem, this condition is equivalent to these partial differential equations for the components of f. And those partial differential equations, those are the Cauchy-Riemann equations. And in one way of defining holomorphic functions, that's the definition of f being a holomorphic function. When I write f as u plus iv, right? If I write it as in a complex way, as this is the real part and this is the imaginary part, then the partial differential equation that these u and v need to satisfy in order for f to be holomorphic is actually, by definition, these guys. Okay, so we're done. So this is just a more geometric way of writing down the Cauchy-Riemann equations. Good, so that then allows us to make this definition that an almost complex structure on a smooth real manifold M is a smooth section J of the endomorphism bundle. What's the endomorphism bundle? It's the vector bundle, which at each point, the vector space is the space of linear maps from the tangent space to itself. That's itself a vector space that forms a vector bundle. So to give a section of this bundle means that at every point, I've got to give a map from the tangent space at that point to itself. And what I want is that this operator squared is minus the identity, right? Because that's what this, if you think about what this J map was doing here, you see it rotated by 90 degrees. So it's this guy rotated here. And if I do it again, then I would be effectively sending V to minus V. The J squared is minus the identity. So we can abstract that property and call that an almost complex structure. Okay. What we're really doing is we're abstracting the property that multiplication by the complex number I has in the complex plane. What does it do? It rotates things by 90 degrees. So I squared is minus 1. I'm taking that equation and I'm sort of geometrifying it. I'm thinking of it as applying on each tangent space. And so I'm wanting to have a candidate for what multiplication by I is on the tangent space. At the moment, I've just got a real manifold, so there's no complex numbers in the game. Okay. So an almost complex manifold is a manifold equipped with one of these almost complex structures, i.e., at every point P, you've got an endomorphism of the tangent space which squares to minus the identity. There's my manifold. At every point P, I've got the tangent space, and I've got a map from the tangent space to itself, such that applying this map twice gives you minus the identity. You can think of it mentally as some kind of rotate by 90 degrees. Okay, so for example, take R2 itself, where J is just a standard rotate by 90 degrees counterclockwise map. So that's going to send the del x basis vector to del y and the del y basis vector to minus del x, as we agreed, right? Del x gets sent to del y and del y gets sent to del x. And that wouldn't have been your only possibility. You could have, for example, sent del x to this funny vector here. And then that funny vector there, that guy would have to get sent to minus del x to make sure that J squared is minus the identity. All right. But this is the standard one. Similarly, on R to the 2n, I can write that as a bunch of x's and a bunch of y's. I can send del x to del yi and del yi to minus del xi. So it's like thinking of it as a bunch of complex planes tied together. R to the 2n, same as C to the n. So those are two examples. Here's a third example. Any complex manifold, meaning a topological space equipped with a holomorphic atlas, it will inherit an almost complex structure, meaning every tangent space of the manifold, you're going to have these you're going to have this operator of squares to minus the identity. So choose a point in the manifold and choose a holomorphic chart around P, or you've got these holomorphic charts by definition because you have a holomorphic atlas. So since I've got all these Z coordinates, each Z is living inside the complex number, so I can write it as X plus IY. So that means I can extract out a bunch of real coordinates, the X's and the Y's of these Z's. Okay. And so now what I'm going to do is I'm just going to set that J of del X gets sent to del Y, and J of del Y gets sent to minus del X. That should have been a minus there. Okay. So what I am saying here, if you've got a complex manifold, then in particular, if you've got an m-dimensional complex manifold, then that means you're also going to have underlying that a 2m-dimensional smooth real manifold, right? And I'm saying on those tangent spaces, you can send del xi to del yi and del yi to minus del xi. That's going to give you this operator on the tangent spaces with squares to minus the identity. And of course, the problem is that this definition of J used a holomorphic chart. So what if I use a different holomorphic chart, Z primes? That means I'm going to have different X primes and Y primes, and I'm going to be sending del X prime to del Y prime. Is that the same operator as this operator? So that's an exercise, really important exercise. Check that this definition does not depend on the holomorphic chart used. Okay. So every complex manifold has an almost complex structure. Complex manifold means having an atlas. That means you have a bunch of charts, whereas a complex structure is just something that lives on the tangent spaces. So the converse is not true. If you have an almost complex structure, then it doesn't necessarily mean that you can enhance that to a complex manifold, i.e. actually find charts for the space such that the corresponding almost complex structure inherited from the holomorphic atlas equals the complex structure you started with. So not every almost complex manifold can be equipped with a holomorphic atlas. Okay, but it's hard to find counterexamples, but this is a very important thing to worry about. But the cool thing is that much of the theory of complex manifolds only needs the underlying almost complex structure and not the holomorphic charts themselves. So you only need the stuff that's living on the tangent space and not necessarily these charts. Okay, sometimes you need the charts. Sometimes you just need the stuff that's living on the tangent spaces. And the stuff that's living on the tangent spaces, that's this J map. So for example, the definition of a holomorphic map, right? Because we can prove this lemma that a smooth map between complex manifolds is holomorphic, which remember in our previous definition, that means you had to go to charts and check that it was holomorphic in the charts. So this is being holomorphic is a concept that's got to do with the charts. Now we're saying that the map is holomorphic if and only if the derivative of f preserves the almost complex structure. In other words, at the level of the tangent spaces, this equation holds. And this equation is only making reference to the underlying almost complex structure. It's not the J. It's not making reference to the charts. So this is so you should prove this exercise, this lemma as an exercise. Of course, it's going to be very closely related to this lemma that we just did. Yeah, so that shows, for example, that the definition of a holomorphic map only requires the underlying almost complex structure to write down. Okay. So here's a nice geometric example. Okay. So suppose you've got a submanifold of R3. So a surface living inside R3. There's an oriented smooth surface embedded in R3. All right. Think of like a torus or something like this. Then the claim is that M is going to inherit an almost complex structure, J, in a natural way by just rotating counterclockwise by 90 degrees in each tangent space. You see, I'm living inside R3. So my tangent space is going to be a plane inside R3. And every time you've got a plane inside R3, you've got the outward pointing normal here because it's an oriented surface. So since you've got this outward normal, it makes sense to talk about rotating counterclockwise by 90 degrees in that plane. So that I couldn't do this if I had to say some abstract surface, right? But because the surface is living in R3, it means I've got these outward normals, and I also have this inner product structure on R3. I can actually talk about rotation by 90 degrees in the tangent space. So that's what I do at each point. So that gives me this operator rotating by 90 degrees in the tangent space at each point. That's going to give me my J. So every embedded surface in R3, oriented embedded surface in R3, in a canonical way inherits an almost complex structure. Then you might ask the question, it's a very natural question to ask, if I wanted to promote this almost complex structure, which is the thing that's living in the tangent space, if I wanted to actually promote it to a holomorphic chart, then the question is, what holomorphic chart would be compatible with this almost complex structure? Okay, that's a nice question. I encourage you guys to think about that and get back to me if you have any more thoughts about that, but we can say some things about that. So for example, we have what's called the Gauss map, okay, which whenever you've got this embedded surface in R3, you're going to have a map from that surface to the two-sphere. Why? Because every point P, I can just send it to the outward unit normal vector at P. Right, so here's my M embedded in R3. Since it's an oriented surface, at each point you've got the outward pointing unit normal vector. And so that vector is a point inside the two-sphere, right? Because it's a vector of norm 1. So at every point in M, I have an associated point in the two-sphere. So I've got this smooth map from M into S2. That's called the Gauss map. And it turns out that this map, this normal map, this Gauss map, maybe I should have called it G, well, it's holomorphic, considered as a map between almost complex manifolds. You see, M is an almost complex manifold. As I said, you've got this J at each point. And S2 is also an almost complex manifold because it's living inside R3. But in fact, we have charts on S2. So S2 is actually a complex manifold. But for now, don't worry about that. It's an almost complex manifold. So it makes sense to ask whether N is going to be a holomorphic map or not. And the claim is that N is a holomorphic map if, but I don't think it's necessary, but certainly it is sufficient, if this M is a minimal surface. The specific kinds of surfaces will have the property that this Gauss map will be a holomorphic map. And what is a minimal surface? So a surface is minimal. One way to characterize it is to say, well, whenever you've got an embedded surface in R3, you've got this shape operator, which is a map from the tangent space to itself at each point. Just like J was a map from the tangent space to itself. Shape operator is also a map from the tangent space to itself, but a different map. What it does is it sends a vector V in the tangent space to the derivative of the normal vector in the direction of V. So if you're over here and you move in the direction of V, then what would happen to these normal vectors? They would start to change direction like this, right? So if you think of their derivative in this direction, you can see what happens when I'm going in this direction. Well, the derivative is, let's think about it. If I'm over here and then I change to over here, then the derivative is to the right. Is that correct? Yes. So the derivative in this direction will actually be sort of in that direction at that point, but at different points, it's going to be different, okay? So that's called the shape operator, and that's a nice linear algebra construct that exists on the tangent spaces of a manifold embedded in R3. That's a certain operator. It turns out to be a symmetric operator, so it has real eigenvalues, and we say that the surface is minimal if the shape operator has its eigenvalues are negatives of each other, so plus minus k. Because usually you're going to have some eigenvalue like 1.6 and some other eigenvalue minus 0.7, something like this. But if the two eigenvalues are opposites of each other, plus minus k, those two eigenvalues are called the curvature components or the principal curvatures. So if the principal curvatures are opposite, then you call it a minimal surface. So for example, the two-sphere itself is not a minimal surface because its principal curvatures in both directions is just 1. So it's plus 1 in both directions. So it's not a minimal surface. So that's why I said that this condition is not sufficient, because clearly the identity map from the two-sphere to itself is a holomorphic map, even though the two-sphere is not a minimal surface. But if M is a minimal surface, then the Gauss map is a holomorphic map. That's a nice, cool fact linking smooth differential and Riemannian geometry with complex geometry. So I love this. I love this little example here. Good. So I've spoken about complex manifolds. I've spoken about almost complex manifolds. And now let's do some almost complex linear algebra. Okay. So forget about manifolds. Let's just put on our linear algebra hats again. So suppose I've got a real vector space V. Then you can complexify it, and I'll write that as V subscript C. By definition, as a set, it's going to be the set of formal combinations of the form given by a vector in V plus I times a vector in V. So this is just a formal algebraic construct. But this is going to form a vector space in its own right, because I can add things like this together by just adding them component-wise. I can multiply them by complex numbers. In particular, I can multiply them in the natural way. So I times this would then give you a minus in front there, and then an I in front of here, and so on. So this forms a vector space, complex vector space in a natural way. Okay. If you didn't like this way of writing it down, you could write it down more algebraically, as to say that it's simply you take the vector space V and you tensor it as an abelian group with the complex numbers. So V is in particular an abelian group. It has a action by R, so it's as an R module. Okay, anyway, if you don't, that's just a formal way of doing it. So where I would make this identification. But yeah, those of you who like this, think about it this way. You can also just think about it like this. All right. Anyway, what do I know about complexifications? The point is, if E1 up to EM is a basis for the real vector space, V, then E1 up to EM will be a basis for the complex vector space VC. So the complexification of V has the same basis. But now remember that over here, you're allowed to multiply them by complex scalars and then take complex linear combinations of these, which give you this vector space, whereas real linear combinations of them give you this vector space. Okay. So just to summarize, V is an m-dimensional real vector space. Its complexification is an m-dimensional complex vector space. Of course, whenever you have a complex vector space, you can think of it as a real vector space as well by just restricting your scalar multiplication to the real numbers. And in that case, if you've got a 10-dimensional complex vector space, it's going to be a 20-dimensional real vector space. So the complexification of V is going to be a 2m-dimensional real vector space, just so that we're all on the same page in terms of counting dimensions here. Okay, moreover, this process is functorial. So anytime if you've got a real vector space V and a real vector space W and a linear map from V to W, then that's going to extend to a complex linear map between their complexifications in the obvious way. Okay, so the exercise, check that everything's kosher there. So now